Hello again, this is lesson 36, actual VCRC and refrigerant properties. The objectives are listed, and what we're going to talk about today is the actual inner workings of a refrigeration cycle. The refrigerant we use, or we're going to discuss, is refrigerant 134A. You can find the properties for this refrigerant in the tables A11 to A13 of our main textbook, or you can use figure A14, which is also called the SUVA chart. However, do not use both. The datum is different for each, so if you go with the tables, stay with the tables. If you go with figure A14, stay with A14. Don't go between the two on the same problem. Alright, because the datum is different. Figure A14 has a note underneath it that states that. Okay, well, I think what we'll do now is knock out the problem that we did in class. Okay, and I'm just going to use some values here for the pressures. The gauge pressures, this was 22 psi, and this was 155 psi, 155 psi, and 28 psi. And so that is P1, so P1 is here. 22 goes through the compressor up to 155 psi gauge, goes through the condenser. Notice that the isobaric assumption is pretty good here, to state 3, where it goes from vapor to liquid, which we saw in the sight glass. It goes through our expansion valve and drops the pressure down to 28 psi gauge. We go through the evaporator, where we go from saturated mixture to vapor again. The assumptions we made are listed here, and this is also the worksheet on page 77 of 84. Okay, so we've discussed the pressures and the states. So now we know all the pressures, and we have some assumptions that we've made. Alright, so let's go ahead and solve the problem. So here's what we're trying to find here. And then our draw picture would be this. Alright, so using our assumptions, we know that the atmospheric pressure is 14.7, the isentropic compressor efficiency, A to C, is equal to 85%. The refrigerant exits the condenser as a saturated liquid, so that means the quality of state 3 is 1. And the refrigerant enters the compressor as saturated vapor, so that means the quality of state 1, I'm sorry, I've got that backwards, is state 1, and state 3 is 0. Alright, so quality of 1, 2, quality of 0 at 3, 4, and we know the pressure is going across, and we know a compressor efficiency of 85%. Alright, so now we can use some math to solve this. So I'm going to find the work in for part A. Because it's per mass and we have one inlet, one exit, steady flow, my equation is enthalpy 2 minus enthalpy 1 is the work required by the compressor. I know for state 1 two properties. I know pressure 1 is 14.7 plus 22 psi, that's gauge, equals 36.7 psi absolute, and I know quality 1 is 1. So those two, I can find everything else. State 2, however, I know the pressure at 2, which is, following the same logic, 169.7 psi A, but I don't know anything else. So I need to find something. What do I know about the compressor? Well, I know the compressor efficiency is 85%. That's my isentropic compression efficiency. So that is the work required by the isentropic compressor divided by the work required by the actual compressor. And this can be written as H2S minus H1 divided by H2 minus H1. Well, since I know H1, or I can get H1, and I can find the entropy at 1, I can get the entropy at state 2. So state 2s is needed, and P2s is equal to P2. Entropy at state 2s is equal to entropy 1. So let's go find these values now. And we're going to use the SUVA chart, which is this monstrosity. Alright, now it's hard to read on this screen. Well, it's hard for me to read. We had state 1, we said it was 22, here's my pressure in absolute, so it's 22 plus 15, so 36, and I'm going to be right about here. Oops. I'm going to go across, and I know, well, let me orient you to the SUVA diagram. What we have here is a pressure enthalpy diagram. This right here is a saturated liquid to saturated vapor line. This is my vapor dome on a pH diagram. pH, pressure, enthalpy. Lines of constant temperature run vertical, hit the liquid line, run horizontal, and then run vertical again. So we can trace 100 degrees Fahrenheit, comes across, hits, and then goes down, and you see the 100 line here. So follow it up, it hits, move over, there it is again. It takes a few minutes just to familiarize yourself with this curve. Density is over here, those lines run that way, pressure is horizontal, enthalpy is vertical, and entropy is this line right here. They run like this. Alright? There's a slideshow that kind of overviews this as well. Feel free to take a look at that. Alright, so I want 36 and a quality of 1. So I want to go across here, hit my saturated vapor line right there, and I'm going to go straight down, and I'm at about 110 BTUs per pound mass. So let's go that way. And unfortunately I cannot write on this one. So we'll say here from SUVA, H1 is 110 BTU per pound mass. Alright, state 2s, now using pressure 2 and entropy 1, we're going to find H2s equals. So let's go back and do that. Pressure 2 was around 160. So here we have 40, there's 100, 200, so 150 a little above. And I want a line of constant, so I'm on this line here. And I want a line of constant entropy from where I was here, about 110 and 35, goes this way and hits about right there. Take it down, I'm about 130. Yeah, about 130. Okay. Okay, and now we can find enthalpy 2, substituting. Enthalpy 2 is equal to enthalpy 1 plus H2S minus H1 over A to C, and that's going to be equal to 133.5 BTUs per pound mass. Alright, so now we have enthalpy 2. Well, let's continue on and finalize this thing. So the work in is equal to enthalpy 2 minus enthalpy 1. It's equal to 133.5 minus 130 BTUs per pound mass, or about 3.5 BTUs per pound mass. Now for part B, we're looking for the heat rejection per unit mass out of the condenser, so Q sub little h. Now that we know state 2, we can find state 3 from our SUVA chart again, where we have the pressure and the quality of 0, and we can find Q sub H. So now we need to find state 3. Now, let's go ahead and write this out, is equal to enthalpy 2 minus enthalpy 3. We know enthalpy 2, we need enthalpy 3. We know pressure 3 is equal to pressure 2, and we know quality 3 is equal to 0. So going back to my chart here, 160 and a quality of 0 gives me a value of, we'll go up this time, 20, 40, how's this run? So we have 20, 30, 40, 50, 60, 160 coming across, hitting this, going straight up. We're at about 20, 30, 40, about 50, maybe a little less, 48 or so, let's say that. Alright, with that, we can substitute in, it's 133.5 minus 48 BTUs per pound mass. And our heat transfer to the high is then 85.5 BTUs per pound mass. Alright, part C. Where am I? Okay, part C. I'm looking for the heat transfer to the evaporator, so QL, the heat absorbed into the evaporator, and this is equal to my enthalpy 1 minus my enthalpy 4 since a heat input. Well, I know enthalpy 1. Let's find state 4. Now this expands or goes around the expansion valve. So if you recall from the notes, the heat transfer from 3 to 4 minus the work from 3 to 4 is equal to enthalpy 4 minus enthalpy 3. There's no heat transfer. We said it's adiabatic. There's no work done. So we're left with enthalpy 4 equals enthalpy 3. Line of constant entropy on the pH diagram is a straight vertical line. Drop that down. Well, this is equal to 48 BTUs per pound mass. Alright, so my heat in to the evaporator is equal to H1, which we said was state 1, 110 BTUs per pound mass minus 48 BTUs per pound mass is equal to 62 BTUs per pound mass. Answer. And then part D, we wanted the COP for our refrigeration cycle. The COP is equal to, what do I want? I want nice cold beverages, so it's Q sub L over my work in, and that is 62 BTUs per pound mass divided by my work in, which was part A, which is 3.5 BTUs per pound mass. I think I made a mistake there. What am I doing? Oh yeah, I'm a moron. H1 is 110, so cancel that out. I'll write it in red. And 110, and that's 33.5. There we go, much better. I tell you. So put another 3 out front here, make that correction, 33.5, and we get a COP of 62 divided by 33.5 of 1.8, which is actually pretty bad, 1.85. So there's my doesn't make sense. Sure, it's greater than 1, which is what we wanted. It's a lower value than you would typically hope for, but that could be due to the readings on our chart, although those are actually pretty accurate, surprisingly. Or it could just be poor performing air conditioner. Okay, so let's do a pH diagram. That's our SUVA chart. So we'll take a look at this. We have pressure on the one side, enthalpy on the other. Recall my vapor dome looks something like this. No, it's more than that. Okay, and we had state 1 at the low pressure line. So let's draw the low pressure lines. And the high pressure line. And then my line of constant temperature, we'll use orange. Orange. Run like this. They run vertical, across, and then pretty much straight down. Vertical, across, straight down. So we said for state 1, we had a quality of 1. This is my saturated vapor line at the low pressure. We moved up at a what we did was we moved up at a line of constant entropy. So this is 1. This was 2s, and 2 was actually to the right of it. To the right of it. So 2 was actually over here. So we moved this way. Then we moved across to my quality of 0 at state 3, and then we dropped isenthalpically straight vertical line on the enthalpy axis to state 4. And then we close it up to 1. So this is what the diagram looks like on a pH diagram, or the SUVA chart. And these were where we got our values to solve our problem. So that's just kind of a recap for you. I know it's hard to read. I apologize for that. And if somebody knows how to fix that, please email me. All right. Otherwise, well, if you know how to fix it, by all means, please email me. Otherwise, that concludes this problem, and hopefully this kind of sheds some light on the actual cycle as it is. There's another sample problem in the student notes. Feel free to take a look at that. And next we're going to see how this cycle, this refrigeration cycle, corresponds to our human comfort, and that's psychrometrics. That's the next few lessons we'll get into. So very interesting how they're tied together. All right, otherwise, have a nice day, and until next time.